Now let's add the last three inference rules to our repertoire of axioms. We've already looked at modus ponens, so let's just have a quick look at that again. So P implies Q, P, therefore Q. So that is modus ponens. And how modus ponens works, if we analyze it using our geometric shapes, is we have a well-formed formula in the square implies a well-formed formula in the triangle. The well-formed formula in the square is repeated, and therefore we can conclude the well-formed formula in the triangle. So that's modus ponens. There is a version there is an inference rule that seems like it's a version of modus ponens. It's very similar, and the schema for it is P implies Q. It's not the case that Q, therefore it's not the case that P. In other words, we have a well-formed formula that implies another well-formed formula. Same first premise. The premise looks exactly the same. The second premise, however, is where things diverge, right? So in the second premise for modus tollens, the negation is applied to everything in the triangle. The well-formed formula that is the consequent of this implication sign, and the conclusion is the negation of everything in the square. So let's look at how that might come up in a proof, or at least the machinery here. So we have P implies Q. Let's do it like this. We have not Q on line 1, P implies Q on line 2, and what we want to conclude is not P. All right, so again, a reminder, this is the setup of the proof. On line 2, we have something that looks exactly like the first premise of either modus ponens or modus tollens. So we have to think, okay, what would be likely to use, modus ponens or modus tollens? But then we notice these negation signs here and there. So let's analyze P. What is that? Well, P actually turns out to be the well-formed formula that is the antecedent of that implication in line 2. Only everything in that square is negated. So if that's what we're after, it sort of matches what modus tollens does. And because of that, we have to look and see what sort of premise we might have to make it work. And sure enough, if we can analyze Q as everything that's in this triangle, the right-hand side of that material implication, and it's negated. So that is exactly the schema we need. We have the first premise on line 2. We have the second premise on line 1, and the conclusion is what we would predict if we apply modus tollens. So we're all ready. Line 3, we're going to conclude not P, and of course the analysis of that follows along with what we just did. So on line 2, we have everything in the square implies everything in the triangle. On line 1, we have the negation of everything in the triangle. And on line 3, we have the negation of everything in the square. Why did I say it in that order? Because that's the order of the schema of modus tollens. So we will write modus tollens applied to lines 2 and 1. And because the conclusion is exactly what we were after, not P, the proof concludes successfully. All right, let's look at another inference rule. This one is pretty straightforward. It's called hypothetical syllogism. We abbreviate it with HS, and its schema is P implies Q, Q implies R, therefore P implies R. So let's look at what happens. We have a well-formed formula in the square implying a well-formed formula in a triangle. That well-formed formula in the triangle is repeated this time as the antecedent of an implication. And we need a new geometric shape, so let's use a circle. So we have a well-formed formula in a triangle implies a well-formed formula in a circle, and the conclusion is everything in the square from the first premise implies everything in the circle from the second premise. Okay, intuitively, this makes a lot of sense. Do a truth table to assure yourself that it's a valid inference. And meanwhile, I'll show you what this looks like. So let's say on line 1 we have R implies S. And on line 2 we have Q implies R. And what we want to derive is Q implies S. All right, so let's analyze this. If you notice here, we have on line 1 and 2, two implications as the premises. So when you look at hypothetical syllogism, you see that it also has two implications as its two premises. So that should make you suspect, I think I can apply hypothetical syllogism to this, to these two premises. And sure enough, when we analyze the premises, what we find is that they follow pretty much the pattern here. We may have to do a little looking, right? So let's consider Q to be the square. So that's the well-formed formula in the first premise. So that must be the triangle, the well-formed formula in the triangle from the first premise. But it's repeated here. Everything in that triangle is repeated. And S is different now, so that we need a new geometric shape, so we have to use the circle. And the conclusion is everything in the square implying everything in the circle. So that tells us that it follows the pattern of the schema of hypothetical syllogism, right? So on line 3, we can write everything in the square implies everything in the circle, just like the schema tells us to. What's in the square? This time it's Q. What's in the circle? This time it's S. We've applied hypothetical syllogism, and the proper order of the premises is lines 2 and 1. So if you look at the schema at line 2, that corresponds to the first premise of hypothetical syllogism. Line 1 corresponds to the second premise of hypothetical syllogism, and this corresponds to the conclusion. Now, since the expression we derived here matches the conclusion that we were aiming at, we have succeeded in constructing a proof for this argument. Now, let's look at one more. This is called constructive dilemma, and it's abbreviated CD, constructive dilemma. So this one has more parts, and it's a little hard to get your head around. But let's have a look at the schema first. This is P implies R, and Q implies S. That's our first premise. The second premise is P or Q. And the conclusion of this inference rule is R or S. So now let's see what's going on here. You've got something in a square. It's repeated in the second premise here. You've got R, which, let's put that in a circle for now. You'll see why in a minute. That appears here. You've got Q, let's put that in a triangle. That appears here. And now we have S, we're going to have to put that in a diamond shape because there are 4, we need 4 geometric shapes, right? So I circled the wrong thing down here. This should have been a diamond instead of a circle. This is our circle. So now look what's happened here. We have P implies R, and P is repeated here. We have Q implies S, and Q is repeated here. But P and Q are joined together by a disjunction. Okay? Now, what a disjunction suggests is that one or the other of these might be true, maybe both, but one or the other of these might be true, but we don't necessarily know which one. What we do know is that we have P implying something and Q implying something. So it's a little bit like modus ponens, but with the or thrown in, because the R and the S are actually the consequence of these two implications. So what we have in a way is we have a conjunction of two implications, and we can assert the disjunction of the two antecedents of those implications, the if part, And we can conclude then the two consequences of those two implications. So in a situation where we have a proof, we could have something like this. P implies R and Q implies S. On line 2, let's have P or Q. And the conclusion we want is R or S. So analyzing this, we've got P. The square is repeated here. We've got Q. The triangle is repeated here. We have R and we have S. And so what we need is the R part and the S part joined together by a disjunction. So what we see is that the overall form of this argument, once we analyze all the parts, exactly matches the schema for constructive dilemma. So on line 3, we can conclude R or S, and our justification is going to be constructive dilemma applied to lines 1 and 2. Because R or S is exactly what we were aiming for, our proof concluded successfully.